So hi everyone, my name is Tomoro Yanase from Max Planck Institute for Meteorology in Germany and University of Hyogo, Japan. I will talk about convective self-aggregation. Most of my talk is a result the concept from the idealized simulations, but the main goal of this lecture is not only that, but also to use this self-aggregation concept for, okay, so maybe I should take this. Okay, so not only the idealized, so not only to understand what happens in the idealized world, but also to use this idealized idea to understand the more general tropical dynamics. So yeah, so maybe, yeah, so that's my point. And this lecture consists of 5 parts. And the first is what is convective self-aggregation and why do we care? And next is how does self-aggregation appears and how do we measure it? The third point is which feedbacks amplify the self-aggregation and what physical mechanism maintain and what sets the scale of aggregation. And the fourth part is a conceptual model, and I will briefly introduce some simple model from the column model to more horizontally extended moisture circulation dynamics. And finally, I will briefly touch on the beyond RCE, not only idealized uniform non-rotating RCE, but also for more broader tropical dynamics and open questions. First of all, what is convective self-aggregation? This is 3D animation from the cloud resolving RCE simulation. Convective self-aggregation is a spontaneous clustering of convective clouds over horizontally uniform lower boundary conditions. And actually, this is simulations over the uniform sea surface temperature, and it is non-rotating, which means there is no Coriolis force, and the domain is doubly periodic, so it's very idealized. But it's this kind of large-scale structure spontaneously happens, so it is interesting. So and the transition from this scattered convection to aggregated convection is what we call convective self-aggregation. And sometimes people call this kind of phase differently. So for example, we use scattered, and sometimes we use disaggregated, disorganized, or random convection. But yeah, basically these terms all refer to this kind of unorganized scattered convection. And we also describe this state by the term aggregated or clustered or organized. But for me, the organized is much broader meaning, so I prefer to use aggregated in this context. So yeah, this is a simple, brief definitions of convective self-aggregation. But if you are interested in more comprehensive review, maybe you may find more good explanation from this review. Yeah, I attached some reference in this slide, so maybe after the lecture, maybe you can find the slide. And as I said, this is simulations of radiative convective equilibrium. So what is radiative convective equilibrium? So it is a statistical equilibrium between radiative cooling and convective heating. And it is originally a 1D particle framework to understand the particle structures of temperature as the one classical, maybe this, okay. So yeah, one example is the Manabe's area work. And but after that, this RCE framework became to be used for studying deep convection in 2D or 3D domains. And Nakajima and Matsuno, 1988, maybe the first studies to use the RC concept to study convective organization. This is a schematic of the RC simulations. And here is, this is one typical setup. This is a 3D domain and horizontally doubly periodic and non-rotating. And typically we use uniform sea surface temperature. And from the warm sea surface temperature, there is the input of energy by radiant heating and sensible heating. And also we calculate the radiation and we use long wave radiative transfer and short wave radiative transfer. But overall effect is cooling. So the radiative cooling destabilize the atmosphere and the convection stabilize the atmosphere. This balance is radiative convective equilibrium. And the domain is typically covers the troposphere, but some studies include the stratosphere, and some studies discuss some QBO-like oscillation, but the typical forecast is troposphere and moist convection within it. Why do we care the convective self-aggregation? One of the reasons is RC is a minimal framework for studying how moist convection, small-scale moist convection interact with radiation and surface flux and circulation, and how they interact each other. So of course, these ingredients plays important role in tropical, real tropical atmosphere, but it's very complex. So it is useful to isolate these interaction in the idealized world. And this is a schematic figure from Nakazawa 1988, and he reported hierarchical structures of intraseasonal variation, and there is a hierarchy from the large-scale intraseasonal variation. And inside the interseasonal variation, there is a supercluster and cloud cluster within it, and also it consists of a small-scale convective element. So RC and the tropical real atmosphere is a bit different, but we hope that basic physics of the large-scale structures of associated with the interaction between moist convection and the large-scale process is included, can be studied in the RCE. So the second part is characteristics and diagnostics. Question is how does self-aggregation appears and how do we measure it? This is a classical example by Rajat in 2005. And this is the horizontal distributions of precipitation and surface flux and the precipitable water. That is a vertically integrated water vapor content. And ORR, and the left panels and the right panels are different timing. And in the left panels, so the precipitations and the moisture and precipitation and convection field shows some organization, but the organization is not so clear. But the time goes on, the convection precipitation is localized in the small space in the domain, and it is associated with high moisture and low OLR, and it is also associated with low-level convergence. And another important characteristic is this convective cluster is surrounded by the clear sky and dry environment. These large-scale structures occurs spontaneously. So this, one simple view of convective self-aggregation is a two-column view. For example, as shown here. And dry subsiding region is characterized by the clear sky and shallow clouds only, and low humidity and high ORR and little precipitation. And the most convective region is characterized by deep convection and high cloud and high moisture and low ORR and enhanced precipitation. The point here is this dry subsiding region and the moist convective region is connected by circulation. There is an inflow into the moist convective region and the outflow from the moist region. So circulation connects these two distinct regimes. So that's a qualitative view, but how do we measure these features more quantitatively? So actually, as Schumacher said, the definition or quantification of the organization is difficult or more, how to say, there is no single answer. It depends on what we know, what we want to know. So different diagnostics answer different questions. So for example, if we ask, when we ask if the moisture is segregated, as we showed before, so we use some diagnostic like the horizontal variance of moisture or some dry fraction rate. Or when we ask the convective element is clustered, we use clustering metric or some organization metric. And when we focus on the circulation, if the circulation is reorganized, we use a metric of related to the low level inflow and some circulation feature. And when we ask what is the length scale, we use spectral or correlation length or some object size statistics. And when we think about the what physical mechanism, what feedback increase the contrast, we use some budget analysis of, for example, the MSE variance budget. So when we think about the quantify the self-aggregation or some more generally the convective organization, maybe we should ask what we want to know. So the question should be clarified before to determine the diagnostic. So each metric quantifies a different aspect of convective self-aggregation. So this is one example of my previous work, and this is this compares vertical time and height cross sections of two scattered regime and aggregated regime. And the shade color displays the horizontal variance of water vapor content. So when we look at the scattered regime, we have some fluctuations of variance of the moisture, but it is not so prominent. But when we look at the aggregated case, so the moisture horizontal variance increases with time, and especially at the lower troposphere. This is the height, and this red color is within the height range from 1 kilometer to 2 kilometers. So the horizontal variance of moisture is especially concentrated in the lower troposphere. And then, this is the moisture's view, and here is the spatial view of circulation in moisture space. In moisture space, specifically here, the horizontal axis is virtual horizontal axis, and specifically we sort the atmospheric current from dry to moist, so which characterize how circulations appears from the dry to moist region. And the vertical axis is height. The left panel is a scattered case. So this dashed line is counterclockwise circulation, and the solid contour is means clockwise circulation. In scattered case, yeah, there is inflow to the moist region like this, but near the surface there is the opposite circulation. And yeah, I will explain later, but it is related to cold pool divergence. So if in the moist region there is a cold pool produced by evaporative cooling, and it produces a divergence wind, and this is a prominent feature of scattered case. But on the other hand, in the aggregated case, this counterclockwise circulation is prominent even in the boundary layer. So this deep circulations sustains the inflow to the moist region. And the clockwise circulation here is limited in the moist region. So if we compare the circulations by using the stream function, so scattered and aggregated states exhibit distinct characteristics. Yeah, this is one of the examples how we measure, how we diagnose the difference of scattered regime and aggregated regime. So the next section is about which feedbacks amplify and maintain and set the scale of aggregations. So yeah, this consists of three questions. They are related but a bit different. The first question onset is if we have small perturbations of moisture convection field, so does it grow or not? So that is a question. And the maintenance means when we have the aggregated state, does it sustain? So that is question. And scale selection means what is the scale of aggregated cluster, and what is the physical mechanism determining the spacing. So that's related but a bit different. So the feedback that triggers the onset aggregation does not necessarily maintain it, so a bit different. And the scale selection has also related to the physical feedback, but a bit different. And also scale selection mechanism. Scale selection has at least two aspects. One is the onset length scale, and also mature, fully developed aggregation state. Yeah, I will briefly touch in this aspect later. So let's first focus on the onset. So the main concept is physical feedback and positive feedback and negative feedback for convective clustering. Yeah, first of all, we think about if we have convective cloud, a single convective cloud, and of course, in the wide domain, so we have many convective cloud. But if we think about single convective cloud, and if some process promotes the new convection in neighborhood or suppressing the new convection in a remote region, it amplifies the contrast, so which promotes aggregation. So it is positive feedback. On the other hand, if some process suppresses new convection in the neighborhood and promotes the new convection in the remote region, so it plays a role for the homogeneous convection field, so which means a negative, which plays a role in negative feedback. So this is a basic idea, and the one example is cold pools. So yeah, if we have convective clouds, we have rain, and if we have rain, there's a rain evaporation, and the cold pools is produced in the lower troposphere. And when cold pool spread, it is known that it promotes the new convection triggering in the vicinity. So it is numerically reported, but also maybe it is supported by some observational studies. That is one physical positive feedback aspect of cold pool. But at the same time, there is negative feedback mechanism of couple. So yeah, if there is a couple, it spread out and it transports moisture from the convective region to remote region. So it is known that it homogenizes the boundary layer moisture. So sometimes it can be considered as a negative feedback. So yeah, one aspect is positive feedback, but one aspect is negative feedback. So we think about both aspects. So it is difficult but interesting point. And the other important feedback is moisture convection circulation feedback. We have convective clouds and it produces a radiant heat release. And also when we have the cloud water, cloud ice, so it produces an anomaly of long wave radiative cooling. It produces a warming anomaly. So it produces, so if we believe the weak temperature gradient, when we have the heating anomaly, it should be balanced by the upwelling motion because it should be the adiabatic cooling balance with diabatic heating. So it produces mesoscale circulation, mesoscale ascent, and it produces the moisture convergence in the boundary layer and free troposphere. And it produces, and also if we have the moist anomalies of free troposphere, it also produces a long wave feedback anomaly. So it it forms some positive feedback. But at the same time, we should care about negative feedback. If we have convective cloud, it removes the moisture from the atmosphere. So it acts as a negative feedback to moisture. So this is also example of we need to think about not only positive feedback, but also the negative feedback. And also, the other aspect is also important. So the moist free tropospheric humidity is related to convective clouds through entrainment and detrainment. Free tropospheric moisture is increased by detrainment of deep convective cloud. And also the free tropospheric moisture's variation enhance convective variability through entrainment because drier free troposphere suppress the deep convective clouds by diluting the updraft parcel, and in moist region, this dilution is mitigated. So it plays role for the positive feedback. So there's no single feedback. So the problem is very coupled network. So many processes are involved at the same time. So at some time, we can focus on some specific feedback, but at the same time, we should remember that the other feedback playing at the same time. So maybe that is, I'd say, not simple, but complicated. But maybe that's one of the essence of this complex system of convective radiative system. That's my point. And this is one example why we should care about positive feedback and negative feedback at the same time, because the onset of self-aggregation can be understood by the competition between positive feedback and negative feedback. Here is again the comparison of aggregated case and scattered case. And the horizontal axis is moisture. So the left base corresponds to dry column, and the right base corresponds to the moist column. And the vertical axis is height. And the shade color is the buoyancy. So which means blue colors means negatively buoyant. And the purple color means the place where the radiative cooling is strong. And the green contours indicates evaporative cooling is strong. So in the scattered case, the evaporative cooling produce in the moist region produce negative buoyancy. So it corresponds to the evaporatively driven cold pool, and it produces this circulation. So as I showed before, this circulation homogenizes the boundary area moisture, and it suppresses the growth of convective self-aggregation. In contrast, in the aggregated case, there is a prominent radiative cooling in the lower atmosphere of dry region. So there is strong radiative cooling in dry region, and it produces a negative buoyancy, and it produces the circulation in this counterclockwise sense. So then it produces the circulation, and it sustains the inflow into the moist region, and it amplifies the moisture contrast, and it acts as a positive feedback of for self-aggregation. So there is a two key players. So the radiative cooling, radiatively driven cold pool, and the evaporatively driven cold pool. They both exist for both cases, but the strength is different. In the aggregated case, this radiatively driven cold pool is stronger effect, and this positive feedback wins, so the self-aggregation occurs. So the thinking about the balance of positive feedback and negative feedback is the important aspect for understanding self-aggregation. And yeah, that was the onset problem, and I will briefly explain the maintenance aspect. So in short, once aggregated, it can persist. Yeah, this is sensitivity experiments conducted by Muir and Hale, 2012, and the horizontal axis is horizontal grid spacing of cloud resolving simulation, and vertical axis is domain size. And the left panel's simulations ensemble start from the homogeneous initial condition, and the right panel shows start from the aggregated state, which is characterized by the horizontal moisture contrast. And if we look at the left panel, self-aggregation is difficult to occur in high resolution, for example, here. So, but when we start from the aggregated state, so even in the high resolution, so the self-aggregation is sustained. So, which means that it is difficult to onset, but it is easy to maintain. So, it is a bit different problem. And also, they also did some sensitivity experiments regarding the radiative effect of low cloud. And they showed that low cloud long wave radiative effect can be important for onset, but it is not necessary for maintenance. So if you are interested in this process, you may look at this paper, but the point here is the onset and the maintenance is different, so we should distinguish it. And finally, yeah, this is a question of spatial scale. At what scale does self-aggregation occurs? Yeah, this is again the sensitivity experiments about regarding the with respect to the horizontal grid spacing and domain size, and for a given resolution, if we increase the domain size, self-aggregation occurs. That in the small domain, so scattered convection is preferred, but if we increase the domain, for example, larger than a few hundred kilometers, it produces the self-aggregation. So it's kind of related to the minimum length scale of self-aggregation. But also, if we increase the domain size more larger, from 100 to 1,000 to 10,000, so the vertical axis is some measure of the length scales of moisture distribution, and it increases as the domain size increases. for the first time. But if the domain size is larger than 6,000 or 10,000, so the length scales of the aggregated clusters converge to 3,000 kilometers. So it is related to the maximum length scales of aggregated cluster. So the onset length and mature distance is a different feature, but yeah, which indicates that there is a scale-dependent physics. So yeah, that's the numerical result. And finally, we will move on to the conceptual model and how we can understand the self-aggregation from by a simple way. First of all, why should we care about conceptual model? So the contents I showed before is about the mostly based on the crowd resolving simulation, but CRM, it is very detailed tools, and it is one of the sophisticated tools for studying, simulating the convective organization, but they are too complex to understand the behavior directly from the governing equation. This is one example of cloud resolving model, and it consists of three-dimensional field of mass and UVW, momentum, and three category of hydrometer and potential temperature. So it's very large number of prognostic variables exist, so it is almost impossible to directly analyze. So we use numerical simulation. It is useful too, but alternatively, we also want to describe the system using a more tractable, simple equation, so that we can interpret the behavior more easily. So this is one example, simple conceptual model. Yeah, if we could derive simple equations, for example, simple prognostic equations of column water vapor by a reasonable way, it is only one single prognostic variable. So it is tractable and we can analyze it more easily. So it is a balance between realism and understanding. So, but one of the important point is, we can interpret the behavior more easily. So I will introduce some different class of conceptual model. The one is a column model, as shown before. So we will think about the atmospheric column, how this column features evolve in time. And sometimes the main variables is vertically integrated static energy or moisture. And we can think about weak temperature gradient or some bistability. The other class is, column is, there is no horizontal structure. But if we want to think about the horizontal structure and what kind of patterns forms, so the one important class is the reaction diffusion equation. This is also based on the column model, but it interacts with other column by horizontal diffusion. And also the other important class is shallow water model. It can represent the circulation field, wind and mass. And important point is it also reproduce the gravity wave propagation. So it is potential to set the spatial scales related to gravity wave adjustment. And also, finally, we will introduce the non-local moisture model. It is a kind of combinations of reaction diffusion idea and gravity wave adjustment idea I will briefly introduce later. And I cannot touch on another class. There is a multi-couple interaction model. It is also important model, but I cannot touch on it in this lecture. But if you're interested in, please see the appendix for the reference. Yeah, first of all, this is a conceptual model of column model. Yeah, the weak temperature gradient is the first point to think about the column dynamics. And the weak temperature gradient can be used as a framework for think about heating and circulation coupling under the weak Coriolis force environment, like equators or some tropical dynamics. And in the weak temperature gradient, the diabatic heating balance with diabatic cooling. It is a fast adjustment in terms of thermal energy, but moisture can evolve with time. So the moisture can be a prognostic variables. Yeah, this is one schematic of weak temperature gradient column. Yeah, this is one column and this is one column. Yeah, moist column and dry column. And if the precipitations and the radiation can be functions of moisture, this is the heating anomaly, cooling anomaly, and it produces vertical motion to achieve the balance between diabatic heating and adiabatic cooling. This is the weak temperature gradient balance, and it can feedback to the moisture field. And then, yeah, some previous studies use this weak temperature gradient framework to think about the moisture evolution. And yeah, this is the one simple idea of moisture, the dynamical system of moisture. And this is, first of all, yeah, if this tendency terms becomes zero, it is a fixed point, it is equilibrium point. But the stability is different. So if the derivative of this tendency term with respect to moisture is negative, it is stable, but it is positive, it is unstable. It is summarized in this figure. Yeah, if we think about this reaction term, this tendency terms can be a function of Q like this. There is 3 fixed point. This can be equilibrium, but this fixed point is unstable. So it cannot be achieved if we have small perturbation. If we have positive perturbation, its perturbation grows and it goes to the other equilibrium point. But yeah, this is we should note that there are 2 stable points in dry side and moist side. So it is bistable. And this bistable state may be related to the dry area and moist area of convective self-aggregation state. This is one important idea from column model. And but in column model, we don't have horizontal distribution, so we cannot discuss the horizontal pattern formation. So the other idea is the reaction diffusion moisture model. And the idea is, this is a simple expression of reaction diffusion model. Yeah, we have reaction term, tendency term, as previously shown, but we also have the diffusion term. And Q moisture field, moisture is horizontally extended. And importantly, diffusion terms, this is the growth rate associated with the diffusion term, and K is the horizontal wave number, and the diffusion term suppress the small scale perturbation. The higher wave number, the suppression is stronger. So the result is if we use the bistable potential for reaction term, and we simulate the time evolution with diffusion term. This is some of realizations of reaction diffusion equation in the time evolution. Here is the initial phase, and this is later phase. And it produced the coarsening, which means dry areas, the size of dry area grows and the size of moist area grows. And it resembles the initial development of self-aggregation of convection. So it is one of the way to think about the horizontal spatial temporal evolutions of self-aggregation. And the other concept is shallow water model, and it can reproduce the gravity wave dynamics. The shallow water equations, this is one example proposed by Bellon 2021, and he has prognostic variables of boundary layer horizontal wind and the geopotential height. And this is a momentum equation, and this is a geopotential height equation. And there is a convective forcing and the large-scale forcing. So by parameterizing the convective forcing as a function of geopotential height, he could produce self-aggregation like envelope of convective clusters. Here is the geopotential height, and there is small scale variability associated with convective heating, but at a large scale, there is a envelope of convective cluster, and there is a large scale circulation. And one of the key physics underlying here is the gravity wave, and the gravity wave can travel horizontally and dissipate, and it plays a role for determining the distance between clusters. So this gravity wave model has some basic physics determining the horizontal scales of mature self-aggregated state. I showed 3 classes of conceptual model, but why do we need some other model? The color model gives bi-stability, so it can produce the difference between moist equilibrium and dry equilibrium, but there's no horizontal structure. And the reaction diffusion model can reproduce the horizontal distribution and as well as the phase separation between dry and moist region. But there is no scale selection mechanism for mature multiple clusters coexistence. And shallow water model gives gravity wave scale selection, and it can reproduce the coexistence of multiple clusters, but there is no moisture feedback. So that is my idea. And non-local, if we combine these ideas, these framework together, and we try to combine these elements to formulate a more unified framework. And this is the conceptual view of non-local coupled moisture model. The prognostic variables is current water paper, and it is there is diffusion and the reaction term, but we think about this reaction term as a non-local coupling term. So which means that we impose the distance of interactions. It means we impose the length scales of how far away one atmospheric current interacts with another. Because in my mind is wing temperature gradient is achieved by gravity wave propagation, but there is finite propagation speed as well as dissipation. So it should be this finite coupling feature should be incorporated in the moisture dynamics if we think about the weak temperature gradient framework. So that's my idea. And by incorporating this non-local coupling idea, we could reproduce the time evolution of moisture And it can reproduce the coexistence of multiple clusters. And it seems consistent with crowd resolving model simulations in a huge domain. So that is one of the class, conceptual model class we proposed. And yeah, we also checked the consistency with the column model framework. For example, the pi stability of the column. And we analyzed the reaction term here. It represents the column dynamics. And yeah, here is the bifurcation diagram of Q. Yeah, horizontal axis is one of the parameters, and this is the environmental mean moistures one column interacts with, and this is parameters, and the vertical axis is Q, and the solid line is a stable fixed point, and the dashed line is a unstable fixed point. So in some certain range of parameters, we could find the bistability, which means the dry equilibrium and moist equilibrium coexist. That is one feature expected from column dynamics. And also, we could find the linearly stable uniform solution. And it corresponds to the scattered convection regime. Convection moisture is uniform, and maybe we have small perturbation, but the overall structure can be staying uniform. So this model has both the scatter regime and convection bistable regime. And we also did some stability analysis for what kind of, what scales of perturbation grows faster. And I don't go into detail, but we derived the effective growth rate as a function of wave number, so the scale dependence. In the precipitation terms, this growth rate is determined by the competition between precipitation term and the divergence term, which is related to the feedback from moisture convection and the weak temperature gradient circulation feedback, and also diffusion. And precipitation terms plays a role for the uniformly damping. So every perturbation can be suppressed by this term, and the diffusion terms suppress strongly for the more higher wave number structures. And this weak temperature gradient divergence term has a high-pass amplification effect, which means a large-scale structure does not grow, but in the large intermediate scale or larger scales, structures grows. By thinking about this, the balance between these three terms, we could derive the selections of intermediate scales structures. So that is the result from the locally coupled moisture model, which incorporates the moisture dynamics as well as the gravity wave finite scale coupling. So the unified view is moisture controls convection radiation, and convection and radiation drive circulation based on the weak temperature gradient balance. And this coupling is formulated as a finite distance coupling. And by formulating this, the column has the bistability of both equilibrium and moist equilibrium. And this amplifies perturbation, but the diffusion and mixing suppress the small scale variability. And their balance controls the onset and scale. So that is one of the framework we propose. So finally, we briefly look at the outlook. Yeah, RG is very simplified framework, and we can step forward to more realistic situation by imposing the dynamical and the boundary forcing. For example, if we add some rotation effect, we can think about the vortex dynamics and TC genesis dynamics. And also, if we think about the planetary scale, RC, or aquaplanet simulation, we can connect the self-aggregation studies to the MGO-like more large-scale disturbances. And also, if we increase the interactive SSD, we can think about the surface energy balance. And we can discuss the ocean atmosphere feedback and how it affects the organization of cloud, starting from the self-aggregation of convection. And we also, if we increase the SSD gradient or large-scale SSD gradient, maybe we can discuss the aggregation in terms of meridional aggregation and zonal direction. And finally, yeah, it is a bit far from the RC studies, but in terms of monsoon convection, maybe the basic physics between moisture convection and circulation would be potentially similar between RC convective self-aggregation and monsoon convection. So maybe that is the hierarchical thinking from RC to more real world. And it is also, yeah, this is final slide, and it is also considered that convective self-aggregation is potentially important for the climate dynamics. And for example, if the self-aggregation, if the convection aggregate more, and if the dry subsiding area increases, so it means that it more efficiently emits the long wave radiation to the space, and maybe it can affect the radiative balance of tropical climates. So it is not simple answer, but it is potential connection to the more climate sensitivity experiment. And there is some observational evidence that if you have more aggregated state, it increases the OLR and the more dry atmosphere. It is consistent with self-aggregation in the idealized simulation. Maybe this kind of observational studies is also important for the future work. And yeah, this is take home. Convective self-aggregation is a spontaneous clustering of deep convection associated with moist and dry separation in RCE. And onset and maintenance and scale selection are related but distinct question. We should care about that. And GSA is associated with many processes and many large-scale feedback, including radiation and circulation and moisture. So we should keep in mind that many feedbacks are going on at the same time. And the conceptual model connects GSA self-aggregation to more broader context of tropical dynamics. For example, the weak temperature gradient, biostability, moisture modes, and gravity wave adjustment, and also non-local coupling. So by looking at the animations of self-aggregation, as I shown before, I'm happy if you think about some physics behind this self-aggregation in the idealized valve. In the idealized valve, in the context of more broader tropical climate dynamics. Yeah, that's all. Thank you.
That was a very nice, comprehensive overview of self-aggregation, and maybe we can take some questions now.
Thank you so much for that talk. I have two very quick questions. My first question is from your very first section of the talk, where you mentioned that you did not use any Coriolis force for the idealized simulation. I think a straightforward question from that is, what do you think will happen if you did have a Coriolis force? Do you think that there's going to be a kinematic versus thermodynamic interplay that affects the aggregation?
Yeah, actually, yeah, typically we don't include the rotation effect, but there is some, many studies include the rotation effect. For example, doing the RC simulation in the F plane. And so, and that simulation creates a TC tropical cyclone-like vortex. And but maybe it is related to the self-aggregation. But some literature argues that, first of all, it's aggregate, like in the non-rotating RC. But if it glows, when it glows, it feels more large-scale dynamical forcing. And after that, it produces a rotating vortex like TC. So maybe there is some connection. So maybe, yeah, we can discuss about some dynamic control and dynamic control in the rotating RC framework. Yeah, that is one of the active research fields. So if you're interested, yeah, nice.
Thank you. I think my second question kind of follows from that. When you said no Coriolis, I just assumed that this was for the tropics or like closer to the equator, just because the Coriolis force is really weak there. And I think my question is, how or is CSA different in the tropics versus subtropics? Because from what I understood, you could probably use the omega tendency equation to come up with the ascent descent thing in the subtropics, but you cannot do that in the tropics. So I guess that's sort of my question of how they're different in
the subtropics.
In the tropics and the subtropics. Is there any latitudinal dependence at all?
Yeah, one way to answer is, yeah, we can change the F parameters. Increasing the F represents the difference of latitude. And that's one way. And how different is difficult. But if we think about the, yeah, if we want to think about the latitudinal difference in a single simulation, we may use beta plane or some more latitudinally varying the Coriolis parameters. So actually, there is some beta planes simulations of related to RC, and it produced a tropical cyclone near the bit far from the equator, and it propagated to the mid latitude. And yeah, so that is one way to connect. But I think so. I think using this framework in isolation for the subtopics is a bit different context. But yeah, we also some hierarchy that imposing substance in this framework. So it is something related to thermodynamic situation of subtropics. So maybe that's one way to think about subtropics.
Yeah, thanks. I guess I was asking if like if there's a difference in like the real world, but it's fine. I think you still answered the question.
Yeah,
thank you.
Maybe we can discuss later.
Thank you for your talk. There is a slide where you are talking about how WTG is used as a tool for heating circulation coupling.
Which WTG? Yeah, this is single.
There is a second point. Diabatic heating balances with adiabatic cooling.
Yeah. This is this is a weak temperature gradient, and yeah, if we think about, yeah, if we could formulate diabatic heating as a function of moisture, yeah, if we have moisture field, we can diagnose heating, and it means that it can diagnose the circulation field as well if we believe the weak temperature gradient. And this circulation field can be feedback to the moisture field through the advection. So there is a moisture equation and the weak temperature gradient equation. Moisture affects the heating and circulation, and it feedback to the moisture field. That is why we can think about the moisture dynamical equations in isolation, even if we use the diagnostic equation of weak temperature gradient.
Where this balance is happening, it is within the cloud or its surrounding environment?
Yeah, it's good question. So what scales weak temperature gradient balance should be applied? So your question is that. So maybe I think this is not only the individual convective abstract, it's more mean, for example, the 1 degree or something like that, and its mean ascent and mean substance can be used for the weak temperature gradient. But I have no clear answer, but maybe that's interesting open question, I think. So which scales weak temperature gradient can be used? Yeah, but this is one way to close the system to the single prognostic equations of moistures. One key idea.
Thank you.
Thank you so much for the talk. I have two very simple questions. First one is like in all the models, like it shows that it starts aggregating and then once it gets aggregated, it maintains in that state in idealized model. So is there any condition or any model setup where the reverse process also takes place, like from aggregated state and it comes back to a disaggregated form?
Yeah, that's good questions. I think if I understand correctly, there is no many literature reporting the reverse. Maybe, yeah, of course, if we impose the moisture anomaly in the initial phase, and as an initial condition, maybe it can go back to the scattered state if the situation is not favorable for aggregation. But if the systems transition from homogeneous state to aggregated state, maybe there is strong tendency to transition to this state. So maybe this state, aggregated state, shows some oscillations or some temporal fluctuation, but it is considered relatively stable. So if we think about, unless there is some external forcing, maybe this state is stable relatively, I guess.
Thank you. I have one other question. It's very generic, like because aggregation, particularly self-aggregation, we only observe in idealized models. But in the real world, there are some studies that state that aggregation takes place in the tropics. How do you think, what is the best way to quantify or measure aggregation in the real world? Because I think the column model, like the simplest column model with moisture or variance of precipitable water or moistatic energy, is not going to work very nicely because it's not a doubly periodic domain and it's not. The real world is not as beautiful as the models. So what do you think can be, out of these, can be the best way to quantify aggregation?
Yeah, that's a good point. Yeah, of course, in RC, there is very strong moisture contrast, but it is not observed in at least in the moist deep tropics. So maybe that is so exaggerated in the RC, but the other way, yeah, this is one example to think about the aggregation in the real world. Yeah, this is a review paper by this Holloway, and it is, it's exactly the same questions observing the aggregation in the real world. And this is one example. Yeah, this is the metric about more related to the convective elements, how it is distributed, how it is close or far. And by using this metric, they could find the relationship between aggregated the degree of aggregation and the OLR or humidity. In that sense, it is consistent with idealized simulation because when we have self-aggregation, it increases the OLR and it reduces the humidity. Yeah, in that sense, it's consistent, but maybe, yeah, it depends on the metric we use. And if you think about some convective clustering metric, maybe we can find some similarity. Yeah, that's the point.
Okay, I guess I'll ask Aneska. Come over here.
All right.
Yeah. Related to the first question, so, and you had this on one of your last slides. So what do you think that ocean coupling would do? So, the time scale of aggregation, occurs over 40, 50 days at a time scale where ocean coupling may be important. Could you kill aggregation with interactive ocean because SST responds to cool in the aggregated region?
Yeah, I think actually there are some work about the interactive SST, and in my understanding, there are two feedback: short wave feedback and long wave feedback. And if the long wave feedback means convective region and the dry region, and there is large cooling effect by long wave radiations, and it cools SST, and which means if we have positive feedback for SST, it supports the aggregation. But at the same time, the opposite feedback applies for short wave radiation because there is clear sky and there is a strong incoming solar radiation. And if this process is stronger, it increases the sea surface temperature and it acts as a negative feedback. So maybe the key point is which of the short wave feedback and the long wave feedback wins. So maybe night times or daytimes differ. So maybe there is variation or something. So maybe that's a key idea, and there is some literature about comparing these feedbacks. So maybe that's the point.
Yeah, if I may add a little comment to that. So Caroline Muller actually tried to get rid of self-aggregation cluster. So I think the best way to rather prevent it, to use homogenized long wave radiation in the model domain. So if I may quote Caroline, she said it's very difficult to get self-aggregation in your model. And once you get it, it's even more difficult to get rid of it.